Welcome students to Lesson 4 of Unit 10, Water and Phase Changes. The learning targets in this lesson are to be able to understand the heating and cooling curve for water and to be able to calculate the energy involved in phase changes. This is the heating and cooling curve for water. All substances have curves similar to this. When water is at a temperature of minus 20 degrees, as we see in the diagram, of course it will be in solid form known as ice. If you're adding heat and the temperature reaches 0 degrees Celsius, the temperature will remain constant until all the ice is melted, and then the energy that's added will cause the temperature to rise again until you reach what's known as the boiling point of water. At this time, temperature remains constant again until all of the liquid water is converted to steam, at which the temperature will begin to rise again. The same type of thing happens as you cool. However, removing heat, the temperature will decrease. Steam's temperature will decrease till it reaches 100. At 100 degrees, the steam will be condensing to form water. Once all of the steam is condensed and is in the liquid state, the temperature will begin to drop again until we reach the freezing point, at which the liquid water will be converted into solid ice. Once all of the liquid is solid, the temperature will begin to drop again. The second plateau we see here in green is the point at which liquid water is being converted to steam. Water is boiling. Normal boiling point is the temperature at which a substance will change from a liquid to a solid when the pressure is at 1 atmosphere. For water, it is 100 degrees. When we see this plateau, we can move backwards and find that temperature on the temperature axis of the graph and find that where that plateau is the normal boiling point. Temperature remains constant during phase changes. That's why we see a plateau here where water is freezing if you're removing heat, or ice is melting if you're adding heat. And then again, a phase change is occurring when liquid water is being heated and converted to steam, or if you're removing the heat, steam is being condensed and converted into liquid. So temperature remains constant during any phase change. When you're looking at the heating and cooling curve of a substance, the first plateau, the temperature at which that's occurring, is known as the normal freezing point. And of course, for water, that is 0 degrees Celsius. In order to calculate energy of phase changes, we need to know the definition of molar heat of fusion. This is the energy required to melt 1 mole of a substance, and for water, the enthalpy or the heat of fusion is 6.02 kilojoules per mole. Molar heat of vaporization is another important concept. It's the energy required to change 1 mole of a liquid to its vapor. Water's molar heat of vaporization, delta H vape, is equal to 40.6 kilojoules per mole. These are two values that we'll have to be reminded of when we are calculating energy of phase changes. Whenever temperature is changing on the slope portion of a heat and cooling curve, temperature is changing, of course we're going to revert back to an equation we've already learned. Heat is determined by multiplying the specific heat of the substance times the mass times the change in temperature. This would be the equation to use anytime you are having a temperature change. That would mean the slopes of the curves. On the plateaus, if it's the lower plateau where we're having fusion or melting, or freezing if you're removing heat, melting if you're adding heat, we will multiply the moles times the heat of fusion to get the amount of energy necessary to make that phase change. On the upper plateau, where when heat is added, the liquid is changing to a gas or boiling, we want to multiply the moles times the heat of vaporization. It can also be the same equation if you are removing heat and allowing water to condense. So with this information, the how to calculate heat when temperature is changing on the slopes, and how to calculate energy involved in heat of fusion and heat of vaporization, we can calculate the energy required to change ice, exactly 42.6 grams of ice, at negative 27.6 degrees Celsius to steam at 856 degrees Celsius. So let's locate where we're starting on our heat and cooling curve here. We're down here somewhere, negative 27.6 degrees, and we want to go way up above our curve to make our steam be at a temperature of 856 degrees Celsius. So we can see how many steps this is going to take. First of all, we're going to be on the slope, the black portion of our curve here, for step 1, where we're going to be heating our ice to the melting point. Then we're going to have step 2 on our first plateau, where we are melting the ice. And then we're going to be on another slope, step 3, where we are heating the liquid water up to the boiling point. Then we're going to be another plateau, step 4, where we're going to be boiling the water, changing it from liquid to a gas. And then finally, step 5, where we're going to have a big temperature change from 100 degrees up to 856 degrees. So there are 5 steps involved here. Let's get started. In step 1, we're going to be using the equation Q equals ms delta T. And so the mass of the ice is 42.6 grams given in the problem. Now the specific heat is of ice, and if you look in your textbook at the specific heats, I think that's on page 297 in your text, you'll find that the specific heat of water is different than the specific heat of ice. It is 2.03, we'll put that in here, 2.03 joules per grams degrees Celsius. So you have to be very careful to remember what physical state we're in here. We want to change this temperature from the given negative 27.6 degrees Celsius up to 0. So that is a change. Remember, we want final temperature 0 minus negative 27.6. So that's a positive 27.6 degrees Celsius change. And when we multiply these together, we're going to get 2,390 joules. And we're going to convert those to kilojoules. So that would be 2.39 kilojoules just for step 1. All right, for step 2, we are going to be using, we're melting the ice. This is about melting the ice. Step 1, I'm going to go ahead and write up here, is about changing the temperature to the melting point, MP, melting point. Step 2 is just about melting the ice. Remember, that's a phase change. So the equation is Q equals, the energy involved is the number of moles times the heat of fusion for water, which we just learned in the previous slide here is 6.02 kilojoules per mole. So we're going to take the 42.6 grams of water, ice actually, but the formula is H2O. The molar mass of water is 18.02 grams per mole. And then for every 1 mole, the molar heat of fusion is 6.02 kilojoules. So our answer is going to come out in kilojoules this time. That's why we wanted to convert step 1 to kilojoules. And the answer is 14.2 kilojoules. All right, now step 3 is going to be involving the change in the temperature to the boiling point. So we're going from 0 to, we're right here in step 3. We're going to go from step 3 right here, from 0 up to 100. So, since we're on a slope, our temperature is changing. We're using the equation again, Q equals ms delta T. The mass is still 42.6 grams. Specific heat of water now, we're in the liquid stage, is 4.184 joules per gram degrees Celsius. And our temperature change is 100 degrees Celsius. And when we calculate that, it turns out to be 17,800 joules, or 17.8 kilojoules. Step 4, we're on another plateau, so this is going to involve water changing into vapor. This is a phase change. Water changing to a vapor. So we're going to take the mass, 42.6 grams, and remember Q equals moles times the heat of vaporization of water, which happens to be 40.6 kilojoules per mole. We just learned that. We're going to divide our grams by the molar mass of water again, and we're going to use that information for every 1 mole of water. It requires 40.6 kilojoules to vaporize it. And the answer to step 4 is 96.0 kilojoules. And finally, step 5 is another slope right in here. So we're going to be using the equation Q equals ms delta T. The mass again is 42.6 grams. Now the specific heat for steam is different than that of ice and water. It happens to be 2.0 joules per grams degrees Celsius times the change in temperature. We're changing, our temperature is at 100, and we want to go all the way up to 856, which 856 minus 100 gives me a delta T of 756 degrees Celsius. When I multiply this, I get 64,400 joules, or 64.4 kilojoules. So now what I want to do is I want to take the answer for each step, 23.9 kilojoules, 14.2 kilojoules, 17.8 kilojoules, 96.0 kilojoules, and 64.4 kilojoules, and I want to add them together because we want to know how much energy it takes to change the temperature from negative 27.6 up to the melting point. We want to melt it. We want to heat it up from 0 to the boiling point, 100. Then we want to boil it or vaporize it. And then we want to heat that vapor up to 856 degrees. So all 5 of these subtotals are going to be added together for the final answer of this problem, which is a sum of, find a little spot to write it here, a total sum of 194.8 kilojoules. Grand total here, our final answer. 194.8 kilojoules. This is the most complicated of all possibilities for calculating energy in phase changes. Sometimes questions might just ask you, how much energy does it take to melt so much ice? Or how much energy does it take to change it from this temperature up to the melting or freezing point, and so forth. It can be any one or more of these 5 steps, but this would be the most difficult of all. Tomorrow in class we will be actually doing a phase change of lauric acid and finding its temperature for which it solidifies. We're actually going to be cooling it, and watching it change from a liquid down to a solid till it freezes. And we are also going to have a worksheet where we can work some problems like this. And thank you for listening, and we'll practice this tomorrow in class.